All right, so now we're going to talk about dually flat manifolds. So let me sort of state a theorem it's like about dually flat manifolds. So when the Riemann-Christoffel curvature denoted by R, right, vanishes with respect to one of the affine connections, then the Riemann-Christoffel curvature R star with respect to the dual connection vanishes as well. And vice versa. Okay. So how do you prove this? So if you recall, it's like what happens, it's like, one way to think about the macroscopic, it's a consequence of the Riemann-Christoffel curvature vanishing, it's like on some domain, is that when you parallel transport in a loop, right, the tangent vector doesn't rotate, okay? So, so when the Riemann-Christoffel curvature vanishes, R is 0, then the round the world parallel transport does not change A. Okay, so A is pi of A along a closed loop. Okay, well, you have to go back to the initial point, obviously, in order to make sense of the comparison. So, we also know, right, that because of the fact that this pair of connections are dual, which is to say that they're metric compatible in some sort of generalized sense, right? So we also know that the inner product between the Riemannian inner product between A and B, right, is equal to pi A pi star B, right? And that's again sort of the sense in which these pair of connections are dual with respect to the Riemannian metric, right? So now it's like what you're going to do, as you might expect, in order to take advantage of this observation that when the Riemann-Christoffel curvature vanishes, if I parallel transport, it's like this vector A around a closed loop back to the initial point, you get A itself, all right? So I'm going to apply that, as you might expect, to this condition. And so, so when this condition holds, right, then this equation becomes that A inner product of B, right, is equal to A pi star B. Okay, for any, but this is true for any A and B. All right, but because this is true for any A and B, it's like it really has to imply that B is equal to pi star B. So this implies that B is equal to pi star B. Okay, which of course implies that the Riemann-Christoffel curvature for sort of this the dual connection denoted by r star, vanishes. So manifold is always dually flat. When it is flat with respect to one of the connections. All right, so and what it means is that there is and then I should say that when M is dually flat, right, there is always an affine coordinate system called that theta, okay, for which that the connection coefficients vanish. And then similarly, there is a dual affine kinetic coordinate system eta such that gamma star ijk respect to this new coordinate system is 0. And then I should say that these coordinate systems induce a basis for the tangent space, which I denote by E sub I, and eta induces which I denote by E super, well, E super I. Okay. All right, and this is consistent. It's like with the convention, it's like which we have for raising and lowering. It's like indices, it's like with the metric. All right. Okay. So how these sort of basis vectors are related is as follows, right? So the Jacobian for the coordinate transforms between the primal affine coordinate system and dual affine coordinate system are defined to be well sort of d eta I, d theta j, and d theta I, d eta j. All right, but in addition to that, they're related to the metric. Okay, so this is equal to Gij, and this is equal to G super Ij. Okay, and of course, in general, right, when you have these change of coordinates, right, and the associated Jacobians, that allows you to transform the basis which is induced by one coordinate system to the basis induced by a second coordinate system. Okay, so this implies that EI, right, in general, right, EJ is equal to, right, so this is just how tensors transform, right? Okay, but because of this, this is equal to Gij EJ, right? And then this, it's like satisfies the fact that EI and EJ, it's like have this raising and lowering operation, it's like involving the metric, okay? So the point here basically is that, you know, it's like if you have a primal affine coordinate system and dual affine coordinate system, they naturally induce, you know, these tangent vectors. It's like in the basis, it's like for the tangent spaces. That's something which always happens, right? But you have a subscript and a superscript, right? And that sort of evokes, it's like this idea that you raise and lower the indices, it's like with the metric. Okay, so the fact that this Jacobian is related to the metric, right, then tells you that when you transform, it's like these basis vectors via the sort of the tangent lift of the coordinate transformation, right, then it actually satisfies, it's like exactly the kind of condition which you would expect, it's like to raise and lower indices. Okay, and the same thing is true when you go the other way, that E super I is equal, or E super J is equal to d theta I, d eta J, EI. And this is equal to, via this relationship, Gij EI. Okay, so this is again, it's like what you would expect to raise and lower indices. Okay, so that is exactly, again, the you know, it's like, it's basically saying that, you know, this idea of thinking of the basis set induced by the affine coordinates, it's like as E sub I, and the sort of the basis for the tangent space associated with the dual coordinate systems as E super I, right? That is perfectly consistent with the notation we normally have, again, relating raised and lowered objects. Okay. So let me state one last theorem before we wrap this up. So the theorem is that in a dually flat manifold, okay, there exists affine coordinates theta and dual affine coordinates eta, okay, such that their tangent vectors are reciprocally orthogonal What I mean by that is that E sub I, E super J is equal to EI G JK EK equals to E, well, actually, I'm sorry. That's actually the proof, right? So that's equal to DI D super J equals to delta, Kronecker delta IJ. Okay. So the proof just follows from this calculation, or this observation which we have here. So let me just sort of briefly state that, because it's pretty straightforward. So the proof follows from these relationships, right? So EI E super J, right, I'm going to use this, is equal to EI, GI, J, E. Maybe I'll change the index. Okay, and then this thing, right? Okay, so you have the Riemannian inner product, these two things, so there's a metric which shows up. So there's a GIK, GJK, and then, of course, those two things are just inverses to each other. So you get the Kronecker delta, delta IK. Okay, so that's really the proof. It's like, and it should be mentioned that obviously the Riemannian inner product, it's like depends on which point you're at. It's like, but this condition holds point-wise at any point. It's like on the manifold, right? So you do have this duality. It's like between this sort of coordinates in some very natural sense. Okay, so let me just stop here for now. Thank you.